Welcome to EPG Pathshala. This is module 2 where we will be talking about symmetric ciphers. In that I will be covering Playfair cipher, Ceasar cipher, advantages and disadvantages, loopholes in Ceasar cipher and Playfair cipher. Symmetric ciphers I have already focused in module number 1, saying that sender and receiver uses the same key. Means for encryption and decryption same keys are used. For this discussion we will have 5 key terms: plain text, ciphertext, algorithm, key and cryptanalytic attack. The next we would be discussing on Ceasar cipher, how the keys are exchanged, and in Playfair cipher how the keys are exchanged. So there are 2 requirements for the secure use of conventional encryption. The first is strong encryption algorithm. Given the algorithm and one or more ciphertext, attacker cannot decode the text or neither find the key. Sender and receiver has to use the same key, so they must have exchanged the key in some way. How the symmetric encryption model works? So message P is a source encryption algorithm. Out of that Y is generated. Y is nothing but encryption algorithm applied to plain text and key is given to that plain text. Decryption algorithm is applied to the ciphertext and what is retrieved is P. What is symmetric encryption scheme? Message P and the encryption key K as an input, ciphertext C is retrieved, which is written as C equal to E in the bracket K and P. Now you know all the conventions. C is the ciphertext, P is the plain text, K is the key and E denotes encryption algorithm. We already assume that the sender and receiver has exchanged the key. So receiver has the key K. Decryption algorithm would be applied, saying that decryption is nothing but K and C, and P would be retrieved back. Symmetric encryption key, what can an attacker do? Attacker is only interested in a particular message, so he or she will try to estimate P dash, that is approximation of the plain text that is being transferred. Attacker may try to recover the key also. So if attacker is not able to find out exact key, he would try to approximate, that is K dash. If K is retrieved, then all further messages can be decrypted. When we talk about any cryptographic systems, they are characterized along 3 independent dimensions. The first is the type of operation that is used to transfer message from plain text to ciphertext, number of keys used, and third, the way plain text is being processed, block cipher or stream cipher. We already talked about these 3 things in module 1. Substitution technique. So substitution technique, each letter of the plain text is replaced by other letter or number or a symbol. Plain text is bit sequence, then ciphertext is also a bit sequence. Let's start with a Ceasar cipher. It is developed by Julius Caesar. The first step in this cipher is it only works on English alphabets. So English alphabets go from A, B, C, D to Z. Alphabets would be assigned a numeric number saying that A would be assigned 0, B would be assigned 1, C would be assigned 2, D 3. It goes on and Z would be assigned 25. All in all, there are 26 characters in English alphabets. So, we started giving number 0, so it goes up to 25. Here comes one more concept, that we need to use modulo 26. Why modulo 26? Because we want our number to be always between 0 to 25. You all know the modulo arithmetic, that if we divide any number by 26, the remainder would always lie between 0 to 25. Here we are, we want a number between 0 to 25. How does a Ceasar cipher works? You have a plain text, go character by character into the plain text and add 3 to the plain text character number, and what you get is a cipher text. For example, I have a plain text called play. Play means P-L-A-Y. Just now I explained how to convert character into a number. So, P takes a value 15, L takes a value 11, A takes a value 0 and Y takes a value 24. Ceasar cipher is simple, add 3 to these numbers. So, P, that is 15, add 3, you will get 18, right. 18 modulo 26 gives 18. 18 corresponds to the character S. So, after enciphering P with the scheme Ceasar cipher, we have got S. The same way you can work around for L. L was represented by a number 11, add a key 3, what you get is 14, that corresponds to the English alphabet O. Then comes A. A has a numeric value 0, add 3, what you end up is 3, that corresponds to English alphabet D. Now comes Y. Y has a numeric value 24, add 3 to it, you get 27. 27 does not correspond to any English alphabet according to our scheme. Once again, let me remind you, the number should be between 0 to 25. This time we landed up with 27. So, here comes the modulo arithmetic for help. You need to do 27 mod 26. When I say modulo arithmetic, you divide 27 by 26 and remainder is 1, and that is what is encipher meant. 1 corresponds to B. So, this time it was tricky. When we had Y, we added 3 to it, it went ahead of 26. So, to get back to our scheme between 0 to 25, we used modulo 26 and it comes to 1. So, Ceasar cipher is represented as C with encryption algorithm K and P. This time we have used key to be 3. Now, what about decipherment? Deciphering is always a reverse process of encryption. So, in encryption, if we have added +3 to the plain text, in the decryption we have to subtract 3 from the cipher text. Don't forget to do modulo 26. Is Ceasar cipher secure? So, let us analyze strength of Ceasar cipher. What about brute force analysis? Try to remember from module 1, brute force analysis is trying all possible keys. How many keys can be there in the Ceasar cipher? There are 25 possible keys. The example which we gave uses only key, that is 3, but we can use 0, 1, 2, 3, 4, 5 up to 25. So, there are 25 possible keys. Encryption, decryption algorithms are known, and the third is plain text language is also known and recognizable. Third point says we use only English alphabets, so we know what our plain text contains. Now comes permutation. Permutation says each element of set with finite elements can be arranged in some other order. N elements can have n factorial permutation. In Ceasar cipher, if we perform permutations, there can be 26 factorial keys are possible. We have new term says monoalphabetic substitution cipher. Monoalphabetic substitution cipher, if per message different substitutions are done, single plain text alphabet to ciphertext alphabet mapping is done, then this approach is called monoalphabetic substitution cipher. Why monoalphabetic substitution? Because it makes brute force analysis difficult, because we have every time used different key for the substitution. Is monoalphabetic substitution secure? No. Frequency of letters can be checked in the ciphertext, and they can be compared to the frequency distribution in English language. For example, if S occurs highest number of times in our ciphertext, then it is equivalent to E. How this relation has come? Because in English language, E occurs many times. Fine. Because A, I, O, they are used many times when you use English language. Letters with high frequency can be mapped with A, I, O, N. The letters with lower frequencies can be mapped with the letters B, Q, V, X. How this analogy has come? Because if you check English language, B, Q, V, X are used less number of times. For frequency analysis, use two letter combination. If we use two letter combination, it is called digrams. Not diagrams, it's digrams. The most common digrams in the English language is TH. Fine. So, if in my ciphertext SY occurs maximum number of time, it can be mapped to TH. So, if we say SYR occurs maximum number of time, we can relate it to THE, that says the. Monoalphabetic ciphers reflect the frequency data of the original alphabet, so they are easy to break. Solution. The solution is provide multiple substitution for a single letter. This scheme is known as homophones. Multi-letter pattern still can be identified. To avoid frequency analysis, two methods are used. Encrypt multiple letters of plain text, and the second is use multiple cipher alphabets. First scheme we will apply to the Playfair cipher, and second scheme we will apply to Hill cipher. Clear? We talked about two methods: encrypt multiple letters of the plain text, and the second is multiple cipher alphabets. Playfair cipher, how does it work? It works on digrams, yani it takes two characters at a time. We are now going to check Playfair cipher in the detail. It works on digrams. So, now you are clear. Instead of single character, we will be using two characters at a time and substitute these two characters with a ciphertext. The Playfair algorithm is based on 5 cross 5 matrix, which is constructed using a keyword. So what is input to this Playfair cipher? Key and the plain text. Output is a ciphertext. So how to construct this 5 cross 5 matrix? As I already emphasized, keyword is given. Keyword we have considered in this example is kingdom. 5 by 5 cross matrix, yani you have 25 blocks. Start putting the key in the block. Kingdom, yani it includes K, I, N, G, D, O, M. So you have 5 columns and 5 rows. Put K, I, N, G, D. 5 columns are over. Then go to the next row and arrange rest of the key O, M. What is the magic in this Playfair cipher? If you have 25 blocks and English language contains 26 alphabets, what would be happening to one alphabet? So the answer is I and J are considered as same character in the Playfair cipher. So if you have I, put J together. So I and J go together. Once you have put your key, now arrange rest of the English alphabet. So start with A, then put B, then C, then check D. D already we kept as a part of key, so skip D, then take E, F. G is already part of the key, so skip H. I also part of key, so skip, then put L. M is part of key, so ignore. Then N is also part of key, ignore. O is also part of key, we have already kept. So now comes P, Q, R, S, T, U, V, W, X, Y and Z. So now you are ready with a matrix. The question arises, if I have a key occurrences, how occurrences is spelled? O, C, C, U, R, R, E, N, C, E, S. What did you observe? There are many repeating characters in this key. What would you do with these repeating characters? You have to skip the repeating characters. Yani in the occurrence, if R has already occurred in the key and you have already kept it in the matrix, next time R comes as a part of key, you need to ignore it. So this is how, with the help of key, 5 cross 5 matrix has been built. Once you are ready with the matrix, the next is how to encrypt. First rule is clear. While you are putting the key in the 5 cross 5 matrix, omit the duplicates. The second is start writing the letters from left to right and top to bottom. I and J are treated as the same letter, and in the remaining matrix can be filled by remaining letters in the alphabetic order. So this I just repeated the steps which we observed during building a 5 cross 5 matrix. Now comes the rules for the Playfair cipher. How would you encrypt the plain text? 2 letters of the plain text are encrypted at the same time, so we have to form the group of 2 letters. Once again there is a trick. If I consider tree, how tree is spelled? T-R-E-E. What I just said, you have to form a group of 2 characters. So my first group would contain T-R and next group would contain E and E. So here also you have to be cautious. Same characters cannot be grouped together. So 2 E's, 2 R's cannot be grouped together. So what you have to do is you have to fill up a character in between the same characters. So T R E E would be now treated as T R, EX, EX. Why did I put X? Not necessary, you can put any character, you can put any replacement, but the purpose behind putting the X is used less number of times in the English language. So, when you decrypt and you find X, you can really omit it to have a meaningful plain text. The third rule is, if two plain text letters are in the same row of matrix, each would be replaced by letter to the right. If it is the last element of the row, you have to perform a cycle and go to the first element to substitute. For example, if you look at my slide, if I want to encrypt RS, R is followed by S. So, R should be replaced by S and S should be replaced by T. So, RS case is clear, substitute them by S and T. But if you talk about T, U, T would be substituted by U, but if you want to check U, who should be substituted for U, you have to cycle and go to the first element of the row, that is Q. So, this is a third rule for substituting when the two plain text letters are in the same row. The next case is when the two plain text letters are in the same column, how would you proceed? So, again have a look at my slide, R and W. R would be replaced by W, the character beneath it, and W would be replaced by I, that is the first character of the column. So, RW is substituted by WI. The rest of the case is clear. If I want to substitute H, A would be substituted by H, that is beneath it, and H would be substituted by S, that is beneath it. Now, the last rule for the Playfair cipher is, if we do not have the case 3 or case 4 applied, we need to check the row and column of the intersection. So, once again have a look, W and D. So, W is the first character to be encrypted. So, check its row and check D's column. When they intersect, that character should be replaced for W. Rule clear? The first character's row should be checked, the second character's column should be checked, and intersecting character is the replacement. When you are working for the D, you have to check D's row and W's column and check the intersection point, that is I. So, WD is in fact replaced by ZI. No wonder you can write ZJ also, because I and J are treated as a same character. Is Playfair cipher secure? Because we use two characters at a time. But it says frequency analysis reveals the structure that can be worked upon by cryptanalyst. So, Playfair cipher is also not secure. So, in module 2, we looked at Ceasar cipher and Playfair cipher. What you observed is they are simple substitution cipher. In the Ceasar cipher, single character was substituted for single character. In Playfair cipher, we grouped the characters together. The group was formed in terms of two characters. But both the ciphers were not secure because of frequency analysis. Frequency analysis can reveal the structure stored in the cipher text. So, we need to still look for the strong encryption algorithms that we will see in the next module.